Hi there. Today we're looking at faster neural network training with data echoing by Dami Choi, Alexander Passo, Christopher J. Shalyu, and George E. Dahl. So on a high level, this paper basically says you should repeat data that's already in memory in order to speed up the entire process of neural network training. And it also says that this can speed up your wall time without hurting your performance too much. And I have mixed feelings about it. So let's jump in. So they basically make a point of saying that machine learning doesn't happen in just one thing. It's not like sklearn.fit anymore. It is more of a pipeline. So what do we mean by this? If you think of something like you want to train an ImageNet model, what you want to do is you have like your data set somewhere, and that could be in a database, it could be in the network somewhere. So if you have even something larger than ImageNet, you'll probably store it on a central server on an Amazon bucket somewhere. So this is in AWS. And the first thing you actually need to do is you need to read that data set. Now, usually, you're not going to have enough memory on a machine to just load in the entire data set into memory. So that means this process here is streaming. So this is continuously streaming data points, and once you have used the data point, you're going to throw it away because you need space for the next one, right? And so the streaming is done continuously. The next process is read and decode. That means you have to, read it from the network and actually bring it into a format where you can use it, usually something like a NumPy array or a TensorFlow tensor. You need to apply some shuffling because usually the order, you can't really trust the order that it is stored in. Oftentimes there is like a bias in the ordering, so you need some sort of a shuffle buffer here. Then often you want to apply some data augmentation to it. That means that you have one image, and we know for these models, if this is your cat, we know for these models that what can help is to basically make many different images from one image. So this could be by cropping part of it and saying, well, if it was a cat before, the small upper right part here is still a cat. So this is one update. It's called data augmentation, and you're going to apply a whole bunch of these things. So you can crop, you can rotate the image a bit. It's still a cat, right? And you can also change its luminance and a bit of its colors. You can jitter the colors. You can horizontally flip it and it'll still be a cat. And that's basically how you make many data points from one data point. And we know that helps. Then what you want to do is you want to batch this data. So you want to put it into mini batches. Since you've shuffled here, that means when the next time the same data point comes along, it's going to be batched with a different group of images, and of course augmented differently with a different group of images, and that basically means it's a different training batch for the model. So this entire pipeline is basically a way that we take data points that we have and we make a whole bunch of variations and various groupings and batchings of it. And we know that helps enormously with the generalization capability of your final models. And then here you apply your SGD update. So that's usually where you forward propagate your data through your network, which here is F. You'll get like some Y hat as an output. And then you have your labels that also come through the pipeline. And you have some sort of loss function, L, that takes both as an input and gives you an output. And then you do your back propagation. So the back propagation would go through your loss function, through your network, and update the network parameters such that your network learned something, right? Now, this step to the right here is usually what we focus on when we do deep learning. The step on the right here, all of this can be done on a GPU, or is usually done on something like a GPU or a TPU, right? But these things are getting faster and faster. The point the paper makes is that the TPUs and GPUs of the world are getting faster, but this entire other thing right here, this is basically CPU land. Now I know there is some data augmentation now happening on the GPU and so on, but in essence you can think of a pipeline where the thing to the left is happening on CPU and the thing to the right is happening on TPU. And even worse, let's say, the speed is continuously increasing. So in your pipeline, the kind of speed would be, so here is the network reading, and here over here is the GPU SGD step, and this is speed. Basically, the further to the right in your pipeline you go, the faster your hardware gets. And that means that since this is a continuous pipeline, right? That basically means that if I input something here, it goes through the pipeline. And even if this is all running in parallel, this thing over here is going to idle. Since this is the fastest part of the pipeline, it is going to just idle a lot, right? Because it can only consume things as fast as this thing can produce. Now, if you have some sort of a multi-GPU machine and just train ImageNet, like you just run the code, usually this is not the bottleneck. Usually your GPUs here are at 100% capacity, so this paper is not for you. But if you are, let's say, a big company, have this network storage, have a big data set, have very expensive data augmentation, this happens, for example, this can happen in NLP and so on. This can be quite your situation, where the earlier in the pipeline, the slower it is. And don't you just love these graphics? So here's time, and apparently it goes in both directions. And so does it go like this? I think what they mean is just time goes in this direction, and you're here, and your upstream. So your upstream is your network. This is your network reading or your pre-processing. And the downstream, this is the GPU. So as you are pre-processing things, and this should be different. It should be, okay, I want to correct this right here. This is idle, and this is running. So as your upstream processes images, right, at the beginning your GPU is idle, but then as soon as it ships off the first batch of images, your GPU can run. Now it's running. While you're doing that, your upstream, your network, is still reading new images, pre-processing them and so on, but it is too slow to insert a batch at the time that the GPU is done. The time the GPU is done, it's still processing this batch, so the GPU is idle until here, where it finally manages to process that batch, and then the GPU is running again. I think that would have been a much better graphic, but you know. So their goal basically is that what you'll have is right here, for example, after the batch. What you'll do is you scrap this connection, you take this, and you put it into a smaller buffer. And the buffer is a repeat buffer. So what it does is it simply will repeat whatever you have in the buffer until something new comes in, right? So new data point comes in, you just output that data point again. For the GPU, it's gonna feel like these are all new batches and they continuously come in, but it's always the same until the next data point comes in, and then you output that one again and again and again and again. Now the actual factor here you can of course tune by hand, or you can just say repeat until something else comes in. In this paper they have an explicit factor where they say we repeat each data point 4 times or 3 times or so on. So this is data echoing. You basically echo the data point multiple times, and this can be done in various places. So they experiment with echoing in any of these places right here. So they experiment with it right here, after reading and decoding, after shuffling. No, I think always before shuffling. Because if you have a shuffle buffer anyway, they say it makes sense that if you do the echoing, you do your shuffle buffer after your echoing. So here, then after augmentation and after batching. So they experiment with these three locations in echoing. Now, what could be the downturn of something like this? The downturn, of course, is that this SGD procedure right here, basically, it relies on the data incoming being an IID sample from your data distribution, right? That's how we formulate SGD, is that there's always new data incoming. Now, if you just output the same data point all the time, that is like no new information, first of all, and second of all, it could bias the SGD update such that because it sees the same data, it sees the same information over and over, it's going to think that's the whole data set, right? So potentially it can make too many steps into the wrong direction. That just happens to be the bias in this particular data point, right? So the IID assumption is invalid. Now, why do you experiment with this in different locations? Because what you expect is that it hurts more or it hurts less the earlier you introduce this. So if you introduce echoing right here, so if you echo your data until new data from the network comes in, it's still going to be shuffled differently, right? It's still going to be augmented differently. So each time the data point comes out of the echo buffer, it is going to be shuffled and it is going to be augmented in a different way than the last time the same data point came out. And it is going to be batched together because you've shuffled differently. It's going to be batched together with a different bunch of data points. And that means SGD gets new information. But if you go onto the very last thing where you just after the batch right here, where you input the echo, that means SGD just gets to see the same batch of data augmented in the same way all the time, right? So of course, where you exactly have to echo, you have to trade this off. So you have to trade off how much you basically violate the IID fresh data assumption against where in your data pipeline is the bottleneck. So if your bottleneck is in the data augmentation, it may make little sense to echo before that because your bottleneck is the data augmentation. And that being said, if the bottleneck is that you don't have enough GPUs, then it probably doesn't make sense to data echo at all. Though their experiments are somehow wonky on this. But so let's dive in. They make the following claims. Let's just go through them really quick. Data echoing reduces the amount of upstream, so think of network reading or augmentation, computation needed to reach a competitive out-of-sample error rate on various datasets and model architectures. Second, data echoing can provide a wall time speed-up in practice. Third, data echoing can support a wide range of echoing factors, and that's the echoing factor is how often you repeat the data. Fourth, the effectiveness of data echoing depends on the intersection point in the training pipeline. Sorry, in the insertion point. That's what our hypothesis was, right? Fifth, data echoing can benefit from additional shuffling after echoing, but does not require it. And sixth, countering expectations, data echoing reaches the same final error rate as well-tuned baselines. So I can absolutely accept 1 through 5, especially in like an actual practical in the wild setting. But 6, we'll see about 6. So let's jump into their models. They sorry about that. They train the following 4 models. So they train a transformer on these 2 datasets, LM1B and Common Crawl. So I guess technically it's 5 models on language modeling. They train the ResNet 32 on CFAR10. They train the ResNet 50 on ImageNet, and they train SSD on Coco. Now here is the accuracies they get, and here is this is the target. So what they do is they train these models, and then they say, okay, what's the accuracy we reach? And then they set a target value. So on ResNet 50, on ImageNet, a very common number to reach is something like 76.5. If you look at, for example, torch vision models, they reach something like this. And so they say, well, our target accuracy here is just a little bit below that. So, and then we just measure how many steps, or how many, their measurement here is fresh data points. So how many actual fresh training samples do we need to reach this target? And this is where it gets wonky, because, for example, take the 91% here on CFAR 10. That is quite low. And also the ResNet 50 is, I mean, this is standard, but still ImageNet is much further nowadays. And I think the effectiveness of something like this has a lot to do with how competitive you want to get. Maybe this is all just an effect of how much under par this target performance really is. And I would expect that, even though they say it doesn't hurt their performance in their experiments, I would at least expect it will hurt your performance in general if you try to get competitive, because these things aren't, as of now, at least the ones I know, like the ResNets, aren't really competitive. But so what do? They measure data echoing with an echoing factor of 2. So that means data that's incoming is output twice in a row. Every data point that's coming in is just emitted twice from the buffer, and then the next data point is emitted twice, and so on. And what they measure, again, is the fresh examples read. So how many fresh data points do you need to achieve something? This is a good measurement because this is kind of independent of hardware. So if you are really in the situation where your GPU is twice as fast as the rest of your pipeline, then an echoing factor of 2 will speed up at most your training procedure by a factor of 2. All right, so you have the baseline in red, and then you have a batch echoing, which is where you echo what we said at the worst possible time, right after batching. So this might hurt your performance the most, but also it has the potential to be the fastest if maybe your augmentation is very expensive. Then, or your batching. You have example echoing after augmentation. So that would mean the augmentation is very expensive, so you save the augmented data point, and then you emit it multiple times, but each time it is batched differently. So it is shuffled and then batched with different other data points. So you have a shuffle buffer after it. And then you have example echoing before data augmentation. So that means the same data point emitted multiple times will be augmented in different ways and basically will lead to slightly different data points. So the results here are pretty much what you could expect, in that the earlier you do the echoing, as you can see here, the more this echoing helps. So the number, for example, this is the object segmentation task. The baseline needs this many fresh examples to reach this target accuracy. With batch echoing, not only do you, with batch echoing, you need less fresh training examples. So that means even though you kind of train on the same data twice, this helps you more, or this helps you. It doesn't help you fully, because the dashed line here is if it would help you as much as a fresh data point, you'd be at the dashed line, right? This is exactly half of this, because the echoing factor is 2. So if a repeated data point was as useful as a fresh data point, you'd be at the dashed line. As you can see right here, you're not at the dashed line, but at least it doesn't hurt. Right? You might expect that it hurts, but it doesn't hurt. It actually speeds up. So the repeated data points at least have some utility. Again, this is only useful if you have this asymmetry in your pipeline. If your pipeline is actually symmetric and you do an echoing factor of 2, the wall time plot would look this for the baseline and then almost twice as high for the batch echoing, because even though it needs the same amount of fresh, or almost the same amount of fresh example, you echo each one twice, so it needs to process it twice, so it'll take much longer. So again, this is useful if you have this asymmetry and if the echoing factor is kind of smaller than your asymmetry. Otherwise, you're simply wasting time repeating data points. Then if you do example echoing here after augmentation, you use even less fresh data points. And if you do it before augmentation, this is really surprising. You almost get the benefit of fresh data points, which is something you might expect, right? Because an augmented, newly shuffled data point is kind of almost a new data point, but still it's quite surprising that you almost get to the level of the theoretical possible. And also here on the ImageNet task, now here is actually an example where you can see that it hurts to do this batch echoing, because the reasons why it could hurt is just that you violate this IID assumption. You basically have correlated data points. This is a big problem, for example, in reinforcement learning, where already by nature of you running episodes and then feeding the episodes back into the training procedure, you have correlated data points, and that hurts your performance here actually compared to the baseline. But then if you go to example echoing and the example echoing before augmentation, again you get a speed up, which is pretty cool. Okay, so they do a bunch of other experiments, and I appreciate these experiments here to really show what's going on and until when can you push this. So here they have a plot of example echoing before augmentation can reduce training time for ResNet 50 on ImageNet. So this is before augmentation, and the echoing factor describes how often you repeat each data point. So this goes from 2 to 5, and you can see that basically you get the speed up. You just sort of get it for free. As you can see, the dashed line again is as if a repeated data point were as useful as a fresh data point, you'd be at the dashed line. And you can see right here that you are just above this dashed line. So this can help a lot. And so this is the fresh examples red, and this is the wall time in their particular situation. In that case, it doesn't help as much, but again, if that very much depends on how the asymmetry in your pipeline is. Now, in these experiments, I would actually appreciate something like they do down here, where I would always like to see where it breaks. So how far can you go with the echoing factor until it doesn't help anymore? Because this sort of tells me pretty much nothing. I want to see where is the low point, where is kind of the optimal echoing factor, and what can you tell me about this optimal echoing factor? How can we determine it sort of beforehand, or how can you reason how does it connect to the different parts of your architecture? So if I had to point out a flaw in this paper, it would be that right here I would expect them to continue this echoing factor increase until it breaks, sort of like they do down here. This is for, I believe this is for the transformer on LM1B. Now here they have a batch size of 1024. And you can see, and this is their standard setting for the transformer, the 1024 batch size. You can see that the baseline uses this many 1.5 times 10 to the 7th fresh examples to train until their target. If you increase the echoing factor by 2, you basically need half as many fresh examples as long as you echo each one twice. again, very surprising, the fact how close you can get to as if each batch were a perfect fresh data point. But you can see as you increase this echoing factor, and here is exactly what I said, right? At some point, this hurts. At some point, you get to the point where the non-IID-ness, the correlation of successive data points, will actually hurt you. And they make a point here of saying that this is, for example, dependent on batch size. Now, in this experiment over here, they have a larger batch size, and here is again the baseline number of data points to reach the target, and you can see again it goes down, but now with the echoing factor, where before you had an increase again, now it continues to decrease. Again, it will be interesting to see where it goes up here and how the number at the lowest, like here the 4 and here the, I don't know what it's going to be, maybe the 16, how this will kind of depend on your batch size. And here is another problem, and that's what I alluded to at the beginning, this performance dependence. Now, I have not read anything differently in the paper, so I had to assume that they trained this here, this number of fresh examples to reach the target is still the target that they determined at the beginning. So it's that 3.9 in the table. That 3.9 was achieved with this batch size, with 1,024. And we know, especially in language models, that larger batch sizes will lead to a better performance, even if you need, let's say, more samples. So here you can see that the samples here it's 1.5 and here it's actually 4 because you increase that batch size. So that will tell you something. 1.5 and 4, that is like a times, okay, that's like a times 2.5. So you go with the batch size of times 4 and you need 2.5 more fresh training samples to reach the same target accuracy. First of all, we know that the larger batch sizes can reach higher target accuracies. So again, these results, the dependence of them on the actual performance to the maximum achievable value, to me, that's kind of a shady world here to always say, okay, how long does it take to reach that particular target? Because we know that this model right here can reach a much higher target, but we don't know this about these models here. What is their kind of performance in the limit? And they try to make these experiments, but I don't really believe them. Maybe, yeah. And yeah, so, and the second, right? That is already interesting. So this ratio right here, this 2.5 to 4. This ratio must mean something, right? I go to a higher batch size, 4 times higher batch size, and I need 2.5 many more fresh training samples to reach the same target. That must somehow tell you something about the usefulness of a single data point versus a succession of data points, right? So it doesn't seem, because I would expect if each data point was valuable, I would expect this to be times 4. And if it were times 1, so if it were no speed up at all, sorry, not times 4, it would be times 1, it would mean I'd need the same number of fresh training samples, right, no matter how I batch them. But it were times 4, that means basically that it doesn't matter really how many training points I have in a batch, as long as I have enough, and the 1,024 seems to be enough. It just matters how many SGD steps I do. So basically what we're saying, SGD isn't getting the most out of these data points. And this ratio, this 2.5, this tells you something about the information content of an additional data point versus the usefulness content of an additional step of SGD. And I would expect that to intrinsically be connected to where the low point of this echoing factor is, because that's exactly what the echoing does. It trades off freshness of data point versus doing more steps on the same information. And for a paper, especially a paper by Google Brain, this is a connection that I would love to see investigated. But enough of the ranting. They do investigate other things. They do investigate, for example, what happens if we just up the batch size. And you can see here, yeah, this is interesting. Even the baseline needs more fresh samples as you up the batch size. At the beginning, this batch echoing, for example, doesn't help. It doesn't hurt, but doesn't help. But as you go to higher and higher batch sizes, this batch echoing starts to help more and more. Again, I believe this is connected to the usefulness of the single data point. At some point, your batch size is just too large for the problem. You'd rather do more steps, and that's why this helps. But also, this model right here might have a higher ceiling accuracy. So, and it is the question whether this model right here has the same, or whether this model right here, the batch echoing model, would actually fall back to the ceiling accuracy of one of these models over here. Yeah, in any case, their point is basically that as you increase the batch size, this echoing tends to help more relatively. Because maybe it's because what I said, right? They say as batch size increases, the performance of batch echoing relative to the baseline either stays the same or improves. While, for example, echoing it either stays the same or it gets, while for example, echoing it either stays the same or gets worse. Dashed lines indicate the expected values if repeated examples were as useful as fresh examples. Yeah, so there's an intrinsic connection here between the usefulness of more data and usefulness of doing additional steps. And here the example echoing, you can almost see it as more data because especially here, you're going to do augmentation on top of it. And you see the non-augmented versus the augmented ratio changes dramatically from here to here. Okay, final set of experiments. As you can tell, this is mostly an experimental paper, and it is always easy to criticize experimental papers, and rightfully so, because I would not trust this very much. But given that it comes from a big institution and it is a very, very well-written paper, I would trust it more than I would a regular paper. And I would say if you're in practice, this is certainly worth trying. Absolutely. I just think that some of the things aren't researched. Like some of my questions aren't answered of this. So they investigate sizes. So they now build shuffle buffers. So you have batch echoing, but they say, but we can do batch echoing with shuffle buffers. So after the batch echoing, right, we have this state where we have the batching, and then we have the echoing. So this is our echo buffer, where we output each data point multiple times. And then we have another buffer, which is a shuffle buffer. Now the shuffle buffer just collects data points and then shuffles them around before outputting them. And that means even though we, output this 5 times, it might not come out 5 times after each other. It might be that it comes out once, and then another data point that was already in the shuffle buffer comes out, and then it'll just say that in total it comes out 5 times. But it is first shuffled together with a bunch of other data points. Of course, this uses more memory, but it returns to that more IID setting. And you can see here as the buffer size increases, then the performance gets more and more to the performance that you would have with completely fresh data, right? So again, trading off freshness and doing multiple steps by basically repeating data points straight out versus repeating data points shuffled. And also here you have the same with example echoing. So if you apply the shuffle buffer to example echoing and you increase its size, you can get very, very, very close to the performance that you would get with fresh data. Which, of course, if you increase the shuffle buffer to the size of the data set, you are at the situation, that's the limit, you are at the situation of fresh data, right? If you do example echoing. All right, so here is where it gets into the funky part, where they say we actually measure the validation cross entropy and the validation accuracy versus the number of fresh examples read. And here I want to concentrate on the ResNet 50 on ImageNet. And as you can see, most of these models, they pretty much end up in the same place here. It's just that the echoing models end up there faster, right? And this is, I mean, this is where it gets a bit confusing, honestly, because why do you have this super sharp thing here? Because usually, and here it sort of speeds up in the middle. You see that, and then it kind of sharply declines. Is this maybe because they dropped the learning rate or something? Now, my main thing is that the performance here, even though this target thing is lower than even though this target thing is the same for everyone, it is lower than the best reachable accuracy. And I'm just, this is just confusing. If this is really true, whoa. If this is really true, I think we have a lot to learn about SGD yet and how we're not actually doing SGD correctly. And because it seems like almost the echo versions are better or reach a better accuracy than the baseline. I don't know, do they just cap it at the performance? I don't think so. I think they say they let it reach. They also have these things right here, these curves where they say this is the best we reach, and this is the ResNet 32 on C410. And again, 91% on C410 is just very, very low. And I'm almost thinking that, okay, this might help if you just throw something that we know is kind of overpowered, because we can reach 99%, or at least you can reach something like 94% on C410 easily with a network smaller than ResNet 32. Maybe this effect manifests if you have actually something that could reach higher, but for some reason you only reach this low. I'm not sure, but this is confusing. And if this is really true, yeah, I would just, if it's true, which I believe this paper, it might be just an effect of not reaching the actual ceiling. And again, look at this. This is just, the curves are just strange, right? You have the echoing before augmentation, like it seems like it's outperforming the fresh data points. I don't know. There's a little bell in my head that doesn't like this. If it's actually true, then, you know, that's cool. But yeah, so my main criticisms are a bit with the experimental methodology, for example, where they increase the batch size but still reach the same target accuracy, even though we know that there is a higher ceiling if you increase the batch size for language models. My other criticism is the non-investigation of this connection right here, maybe. But all in all, it's a pretty cool paper. If I had a big company with these pipeline issues, I would absolutely implement this. This seems like a no-brainer to do this and can help you tremendously. All right, that was it. Thank you for listening. If you're still here, subscribe, like, tell a friend. Bye-bye.